Hello, ladies and gentlemen. Today we are going to be completing a reaction review. You're going to complete this on a separate piece of paper and take down some notes. So the first type of reaction that we are going to begin looking at are single replacement reactions. Remember, we can use the pattern to identify single replacement reactions. In a single replacement reaction, it's always AB, so a compound, plus C, an element, will yield A, C, and B. You see that B and C, these two elements traded places. And remember, they trade places based on their charge. So an example of a single replacement reaction is the one found below. So this first example uses zinc. If you guys remember, zinc is a transition metal. You guys do have this separate piece of paper on the back that has some information, which includes zinc. Zinc has a positive 2 charge. Remember, guys, don't forget that this information is here on the back. This is always where I recommend looking first. So we know zinc has a positive 2 charge. Hydrogen, because in column 1, has a positive 1 charge. Chlorine, because it's in column 17, has a negative 1 charge. And then we do some swapping of places. Remember, we swap places based on their sign of charge. So we'll swap the places that have the same sign. So on the product side, you'll see that zinc will be where hydrogen is, which is bound to chlorine. So remember, we would have to crisscross. We already said zinc has a positive 2 charge. Chlorine has a negative 1. We would bring the charges to the opposite sides, so the first one becomes ZnCl2. We then have H going where zinc is alone, which is H2. Remember, the reason why this 2 is here is because it's diatomic. Diatomic molecules do not want to be alone. Instead of being alone, they will react with themselves, and there will be a little 2 there anytime that element would appear alone, not when it's in a compound. When they're alone, we include a 2. When it's in a compound, we crisscross charges. The next example is and then we would have to balance. I can't believe I almost forgot to balance. So now we start on the left side. We see there's 1 zinc. On the right side, there's 1 zinc. We check the hydrogens. On the left side, there's 1. On the right side, there's a 2. So that means we include a 2 in front of the HCl from the left side. Now we check our chlorines. There's 2 chlorines on the left side, and there's 2 chlorines on the right. So we know this is balanced, and we are ready to move on. Next, we have our double replacement reaction. Remember, again, we identify this with the pattern. In a double replacement reaction, it's AB, which is a compound, plus CD, another compound, which yields AC and BD. So this is really, really similar to single replacement, except this time we have 2 compounds. So again, 2 elements. They will trade places. Remember, in a double replacement reaction, it's always the positive elements that trade places. So we need to go through and identify the charges. So this time I'm not going to use the periodic table. If you need help identifying charges, please let me know. So sodium has a positive 1 charge. Chlorine has a negative 1. Cadmium has a positive 2. And nitrate has a minus 1. Remember, guys, the charges for both of these were found on the back of our periodic table. Don't forget that list exists. Make sure it's been given to you. Make sure you use it. So then next, we see that the same sign charge elements will trade places. So that means it's cadmium and sodium. They're going to trade places. So that means on the right side, we're going to have sodium go where CD is. So then when sodium is bound to nitrate, we need to crisscross. Na has a positive 1 charge. Nitrate has a minus 1. We then crisscross, bring the 1s down. We see it becomes Na and O3. We then do the same thing. So we go cadmium. It's going to be where sodium is, bound to chlorine. Cadmium has a positive 2 charge. Chlorine has a negative 1. We then crisscross. We bring the 1 to the left, the 2 to the right. It becomes CdCl2. Now we have to go through and balance. When you're balancing your reactions, especially when we're working with polyatomic ions, remember, we keep the polyatomic ion together. We're going to balance the nitrates on the left side and balance the nitrates on the right side. We're not going to balance nitrogen and oxygen. We balance them together as nitrate. So let's start with sodium. 1 sodium on the left, 1 sodium on the right. So far, so good. Now let's check chlorine. So on the left there's 1 chlorine, on the right there's 2. Oh, so that means we have to put a 2 in front of the NaCl. Remember, when we add coefficients, we need to check how that affects things. So that tells us we now have 2 sodiums, because 2 times 1 would give us 2. So that means on the right side, we now need to add a coefficient over here because there's only 1. So we put a 2 in front, because again, 2 times 1 equals 2. We also have 2 nitrates, because 2 times 1 equals 2. Don't be confused by this 3. That 3 is a part of nitrate, so really this is in parentheses with a 1 on the opposite side, on the outside, because remember this number tells us how much we have of what's on the inside, and NO3 is nitrate. You need 3 oxygens, so we can't break it up. So then we see there's 2 nitrogens on the left, there's now 2 nitrogens on the right, so that means this reaction is now balanced. The next reaction, this reaction is a combustion reaction. So again, we can use the pattern to identify the reaction. Our combustion reaction is always a hydrocarbon reacting with O2. So O2 is easy to remember, it's O2. Hydrocarbon is also easy to remember, don't be confused. It sounds exactly like what it is, hydrogen and carbon. Some amount of hydrogen bound to some amount of carbon. Remember, I wrote the products in. I wrote the products in because every single time you have a combustion reaction, the products are the same. They're CO2 and H2O. Now the only thing we have to do is go through and balance the combustion reaction because, remember, based on the amount of carbon and hydrogen we have, that makes it so then we have a similar amount of carbon dioxide and water. If you increase the amount of carbon and hydrogen on the reactant side, then you increase the amount of products you make. It's just like cooking. If you're going to go and make a pizza and you have more ingredients, you have more dough, sauce, cheese, you're going to be able to make more pizza. Same thing here. You have more carbon and hydrogen, means you're going to have more oxygen, which means you're going to make more carbon dioxide and water. So now we go through and balance. So there's 5 carbons on the left side, there's 1 on the right, so we add a coefficient of 5. Same thing for hydrogens. There's 16 hydrogens on the left, there's 2 on the right, so this time we add an 8, because 8 times 2 gives us 16. Now we need to balance the oxygens. Remember, when we balance the oxygens, there's oxygens in both CO2 and H2O. So we need to find the total by adding up the oxygens in carbon dioxide and adding up the oxygens in water. So we have 10 in CO2, there's 8 in water, which gives us a total of 18 electrons. Remember this 10 because 5 times 2 equals 10, 8 times 1 equals 8. So then that tells us on this left side we need to get to 18, I don't know why I wrote electrons, I meant to say 18 oxygens. So that means we need to get to 18 oxygens. So then we ask ourselves, what times 2 is 18? And the answer is 9. So then 9 times 2 is 18, so we add a 9 in front. The last 2 types of reactions are synthesis and decomposition. These reactions are opposite of one another. So synthesis is when we have 2 elements combining to form one product. Decomposition is when we have one product that breaks up in its different ions or elements. So the first example, we have Ca plus N2. So we see we have an element and a lone element. Remember, this is a lone because it's diatomic. And it's going to form a new compound, calcium and nitrogen combined. So remember, when we do this, we have to crisscross. Calcium has a positive 2 charge. Nitrogen has a minus 3. Bring the 2 to the right, the 3 to the left. So the formula becomes Ca3 and 2. Now we go through and balance. We realize there's 1 calcium on the left, 3 on the right. So we add a 3 in front of the calcium. We check the nitrogens, 2 and 2. So we're good. Remember, guys, synthesis and decomposition are opposites. So that means Ca3N2 is just going to be breaking up into its elements. So this can break up into Ca, and it can break up into N2. Remember, guys, these subscripts. So this has a subscript because it's diatomic. This is not diatomic, so it's alone. So this is a good example because lots of times I'll see people carry over this subscript. Remember, this subscript over here came from crisscrossing the charges. So there's no crisscrossing happening, so there's going to be no subscript. So instead of balancing by adding subscripts, we balance by adding coefficients. So we see on the left side there's 3 calciums, on the right side there's 1, so that means we'd add a 3. And then we check the nitrogens, 2 and 2. So it balances. Like always, guys, if you have any questions, please bring them to class. I hope everyone has a wonderful day. Bye.